Good morning, students. Welcome to Bindu Dhadwal chemistry lessons. Our topic for today is S block elements, some important compounds of sodium. Along with that, we will do the introduction of group 2 elements, alkaline earth metals, and their physical and chemical properties. So let's begin. So the first compound of sodium is sodium carbonate, and it is commercially also known as washing soda. The formula is Na2CO3.10H2O, and it is prepared by Solvay's process. Uses of washing soda are, it's used in water softening. Then it is used in manufacture of glass, soap, borax, and caustic soda. It is used in paper, paints, and textile industries. Then sodium carbonate is an important laboratory reagent both in qualitative and quantitative analysis. Sodium chloride, another compound, is also known commonly by the name of common salt, rock salt, table salt. They all contain this ingredient NaCl, so chemical formula is NaCl. So it's used as a common salt or table salt for domestic purposes. In cooking, it's an essential item. It is used for preparation of caustic soda, sodium hydroxide, and washing soda, Na2CO3. The next compound is sodium hydroxide, also known as caustic soda, and has the formula NaOH. It's used in the manufacture of soap, paper, artificial silk, and a number of chemicals. It is used in petroleum refining, in the purification of bauxite. Sodium hydroxide is used. Bauxite is Al2O3. So when we dip it in NaOH, it forms a soluble salt, sodium aluminate, and impurities are insoluble and can be filtered and so purified. In textile industries for mercerizing cotton fabrics, NaOH is used. For preparation of pure fats and oils, it is used, and it is also used as a laboratory reagent. Then sodium hydrogen carbonate, commercially known as baking soda. Its formula is NaHCO3, so it is used for baking purposes like cakes, biscuits, pastries. It's used as a mild antiseptic for skin infections, and in fire extinguishers, it's widely used for production of carbon dioxide. Then group 2 elements are alkaline earth metals. The members of this family are beryllium, magnesium, calcium, strontium, barium, and iridium. Apart from beryllium, the other elements, they form the group alkaline earth metals. They are called alkaline earth metals because their oxides and hydroxides are alkaline in nature, and these metal oxides are found in the earth's crust. So hence the name alkaline earth metals. They are metallic in nature. Then you can remember the elements of this group with this beta mange car scooter baproe. So Ba beryllium, Ma Mg magnesium, Ca calcium, Srs strontium, barium, and radium. Electronic configuration of the elements. It's the general electronic configuration is that of a noble gas and NS2. For example, beryllium has 1s2, 2s2, magnesium 1s2, 2s2, 2p6, 3s2, calcium 20, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Similarly, strontium will have 5s2 in the end, barium will have 6s2 in the end, and similarly radium will have configuration of radon and 7s2. So outermost electronic configuration, 2 electrons in the outermost shell. S subshell of outermost shell. Atomic and ionic radii. So this alkaline earth metals are smaller in size than the alkali metals, and down the group the radius, metallic radius, will increase, and ionic radius will again increase. Atomic and ionic radius of alkaline earth metals are smaller than those of corresponding alkali metals in the same period. This is due to increased nuclear charge in these elements. For example, alkali metal lithium has 3 as nuclear charge. Beryllium has higher nuclear charge, though they have the same number of shells. So more positively charged particles means they will attract the outermost electrons with greater force and the size will become smaller. Within the group, the atomic and ionic radii increases with increasing atomic number. Ionization enthalpy. The alkaline earth metals have low ionization enthalpy due to fairly large size of the atoms. So, because atom is large in size, so it's easier to take out the outermost electron. Less energy is required, so ionization enthalpy is low. And since atomic size will increase from top to bottom in this group, so ionization enthalpy decreases. For example, the first ionization enthalpy is 899, and as we go down the group, the ionization enthalpy value decreases. Similarly, the second ionization enthalpy value also decreases. Now, the first ionization enthalpy of alkaline earth metals is greater than that of alkali metals, higher than that of alkali group 1 metals. This is because they have smaller size, so it's greater energy is required to pull the electron from the outermost shell as nucleus is holding it tighter. The second ionization enthalpy value of alkaline earth metals are smaller than those of corresponding alkali metals, because in alkali metals their outermost shell has 1 electron. Once it is removed, to remove the second electron will be removed from a stable noble gas configuration, so higher energy is needed. Whereas in case of beryllium, after removal of 1 electron is still left, and to remove this electron it will be easier because after removal a stable configuration is achieved. So second ionization enthalpy of alkaline earth metal will be less than that of alkali metals. Hydration enthalpy. Alkali metals, the hydration enthalpies of alkaline earth metals ions decreases with increase in ionic size. Alkali metals में भी ऐसे ही होता है कि जब नीचे जाते हैं तो जो हाइड्रेशन एंथैल्पी की वैल्यू है वो डिक्रीज होती है, और अल्कलाइन अर्थ मेटल्स में भी होता है. वाई इट डिक्रीजेस? क्योंकि साइज इंक्रीजेस. तो स्मॉलर जो आयन होता है उसको वाटर मॉलिक्यूल्स ज़्यादा अच्छे से सराउंड कर पाते हैं और एनर्जी रिलीज्ड ज़्यादा होती है ये, इसलिए हाइड्रेशन एंथैल्पी जो है जैसे जैसे नीचे जाते हैं साइज इंक्रीज करता है तो कम होती जाती है. The hydration enthalpy of alkaline earth metals are larger than those of alkali metals because size is smaller. Compounds of alkaline earth metals are more extensively hydrated than that of alkali metal. So magnesium chloride is hexahydrated, MgCl2 6H2O. In comparison, alkali metal halides, NaCl, does not show hydration, does not show a hydrated compound. It's not hydrated. Similarly, calcium chloride, hexahydrate, we have with alkaline earth metal. KCl is not hydrated. Physical properties of alkaline earth metals. Alkaline earth metals are silvery white, lustrous and relatively soft metals, although they are a little bit harder than alkali metals. Beryllium and magnesium show somewhat grayish color. Then melting and boiling points of alkaline earth metals is greater than that of alkali metals because of their smaller size. The trend of melting and boiling point is not very systematic. Beryllium has higher melting point, magnesium has less, then it increases, then again decreases, and so it's not systematic. Similarly, boiling point also varies. Because of low ionization enthalpy, they are strongly electropositive in nature. Alkaline earth metals, for example magnesium, because of low ionization enthalpy, will easily give electrons to form positively charged ions. So they are electropositive in nature, and the electropositive character increases as we move from beryllium to barium down the group. These alkaline earth metals show characteristic flame test. In the flame test, they show characteristic color. For example, brick red for calcium, crimson for strontium, and apple green for barium. They will impart this color to the flame. Why they impart color? Because when these alkaline earth metals, they are placed in the flame, the energy of flame is sufficient to excite the electrons to higher energy levels. And when these excited electrons fall back to the ground state, they release energy in the form of visible light. So they give color. So according to the difference in the two energy levels of the ground and excited in different metals, the color is different. Beryllium and magnesium, the first two members, do not impart color to the flame. This is because the electrons are too strongly bound to get excited from the energy of the flame. The energy of flame is not sufficient to excite the electrons of beryllium and magnesium to higher energy levels. The flame test for calcium, strontium and barium is helpful in the detection in qualitative analysis and estimation by flame photometry. Then alkaline earth metals have high electrical and thermal conductivities, just like alkali metals. Chemical properties of alkaline earth metals, they are much less reactive than alkali metals. The reactivity will increase on going down the group. Beryllium and magnesium. So first property is reactivity towards air and water. So beryllium and magnesium are kinetically inert to oxygen and water, because they form a film of an oxide on their surface. When they react with oxygen, a film of oxide is formed on their surface, which prevents the attack of air and water further. But if we powder, then powdered beryllium and magnesium will burn. Beryllium will burn brilliantly on ignition in air to give beryllium oxide by reacting with oxygen of air, and beryllium nitride by reacting with nitrogen of air. So beryllium plus nitrogen will give beryllium nitride. Magnesium powder also is more electropositive and will burn with dazzling brilliance in air to give the respective compounds magnesium oxide and magnesium nitride. Then the next member, calcium, strontium, barium, they will be readily attacked by air to form oxides and nitrides, and they can also react with water and with increasing vigor even in cold and form hydroxide. So calcium plus water will form calcium hydroxide. Reactivity increases down the group. Then reactivity towards halogens. So metals react with halogens at elevated temperatures to form respective metal halides. The metal can be beryllium, magnesium, calcium, strontium, barium. And similarly, the halogen can be fluorine, chlorine, bromine and iodine. For making beryllium halide, beryllium chloride, this method with thermal decomposition of ammonium beryllium fluoride is the best route for preparation of BeF2 is BeO2 beryllium oxide plus carbon plus chlorine at a temperature of 600 to 800 Kelvin will form beryllium chloride and carbon monoxide. Reactivity towards hydrogen. All the elements except beryllium combine with hydrogen upon heating to form their hydrides MH2, MgH2, CaH2 and so on. Beryllium hydride can be prepared by reacting with lithium aluminium hydride. We will react beryllium chloride with lithium aluminium hydride. So beryllium hydride will be formed. Along with that, lithium chloride and lithium aluminium chloride will be formed. Reactivity towards acids. So alkaline earth metals react as typical metals and displace hydrogen from acids. For example, alkaline earth metal plus Hydrochloric acid will give alkaline earth metal chloride and hydrogen. Reducing nature, like alkali metals, alkaline earth metals are strong reducing agents. This is indicated by their large negative values of reduction potential. Beryllium minus 1.97, down the group it increases minus 2.36 to 2.92 respectively. However, their reducing power is less than that of corresponding alkali metals. Among these, beryllium has less negative value as compared to other alkaline earth metals, but still it is better reducing agent in nature due to more hydration energy associated with it because it's smaller in size. So it's better reducing agent because of small size and greater hydration. Small size of beryllium ion and relatively large value of atomization enthalpy and large hydration enthalpy will make it a better reducing agent. Solutions in liquid ammonia, like alkali metals, alkaline earth metals will dissolve in liquid ammonia to give deep blue-black solutions forming ammoniated ions. So alkaline earth metal plus ammonia. Of this much ammonia, X molecules will combine with the cation to form ammoniated cation, and Y molecules will surround the electron to form ammoniated electron. So because of this, they give a deep blue-black solution and they are conducting in nature. From these solutions, the ammoniates, metal hexaamine, can be recovered, complex ion can be recovered. Uses: beryllium is used in alloys. For example, copper beryllium alloys is used in manufacture of high-strength springs. Then metallic beryllium is used for making windows of X-ray tubes. Uses of magnesium: magnesium is used to make alloys with aluminum, zinc, manganese, and tin. Magnesium aluminum alloys, being light in mass, are used in aircraft construction. Magnesium powder and ribbon is used in making of flash powders and bulbs, and in making incendiary bombs and signals. A suspension of magnesium hydroxide in water, called milk of magnesia, is used as antacid in medicines for reducing acidity. Then magnesium carbonate is an ingredient of toothpaste. Calcium. Uses of calcium: it's used in the extraction of metals from oxides which are difficult to reduce with carbon. If carbon cannot act as a reducing agent, we will use calcium to convert metal oxide into metal. Calcium and barium metals, owing to their reactivity with oxygen, nitrogen at elevated temperatures, have often been used to remove air from vacuum tubes. Then uses of radium. Radium salts are used in radiotherapy, for example, in the treatment of cancer. That's all in today's video. If you like the video, please do share and subscribe. Thank you. Have a nice day.